In this step-by-step guide, I'm going to show you repeated measures t-test analysis. In this case, is about a pre and post design. So participants have a measurement on a dependent variable. Let's say it's they are reading abilities, and these are the pre-intervention is the result. These are the values they have before an intervention, and then they go through some training, and then we've got the post-intervention results on the dependent variable. Now, unfortunately, the way that JASP does this is same as SPSS, and we don't have the name of the dependent variable in anywhere here. That's in the repeated measures designs. We don't have the name of the dependent variable. So we have the name of the independent variable. The two values are pre-intervention and post-intervention. But that's the traditional way of doing this analysis. JASP adopted the SPSS style here. Okay, so then you go to t-test, pair samples, t-test, and then you need to put the pairs, pre-intervention, post-intervention. I've got the difference, but that would be useful to have some statistics, but you don't need these, and typically in your dataset you won't have these difference. And again, JASP is very quick at calculating the t-test. So pre-intervention, post-intervention, t-test of 3.8. Degrees of freedom is 29 because we have 30 participants that they went through this pre-intervention and post-intervention. And then we can have descriptive statistics. So 30 participants, the mean performance, it was 30.8 pre-intervention, and the performance was 28.2 after intervention. And this is the standard deviation. Now, basically there was a reduction in value, but let's say that this performance is the number of errors you make. So the post-intervention is a reduction in error. So that's an improvement. And we've got the t value 3.8. The degrees of freedom is 29 because there were 30 observations, and the p value 6.9 e minus 4. So remember, when you have this scientific notation, what you have to do if it is negative is to move the period 4 places to the left. So it would be 0.00069. And then we can now also important is what hypothesis you have. If the hypothesis was that there will be a difference, and you don't know whether the difference is an improvement or it goes backwards, so it's a decrease in performance. If you don't know, then it should be this alternative hypothesis. Now, typically in intervention studies, your hypothesis is that there will be an improvement, that you do the intervention, you want to test the intervention, and you do run the experiment to see whether it works. So typically you are justified to have a directional. And in this case, if our prediction is that there will be a reduction in error, so if the dependent variable here is error, then you have to say that the hypothesis will be that measurement 2, the values of measurement 2 will be lower than the values of measurement 1, so that would be the case. And then we've got a one-tail t-test. So we've got 0.00034. That's the p-value. Now, sometimes you may have you expect a reduction and you get an increase, or the other way around. So if you expect an increase here, the p-value will be 1. So basically, the probability that this study comes from a null hypothesis, from a population in which the null hypothesis is true, is 1. So, or it should be close to 1, but by rounding is just is putting 1. So very important what you put here, and that is not something that you decide after the study. This should be decided before the study. You cannot change what was your hypothesis after observing the data. Then we can have the location parameter that will tell us the mean difference. And so here is the pre-intervention minus post-intervention. And the mean difference is 2.6, standard error, and we can put the confidence interval there. That's the confidence interval of the mean difference. And then we can have a descriptive plot where we have pre-intervention, post-intervention, and the bar identifies the 95% confidence interval of the values of pre-intervention and post-intervention.